Hello and welcome to this video on stoichiometry, the weirdest word you're going to interact with in chemistry and most of the math that you're going to see in this class. But here we go. This is going to be a gentle introduction to get you comfortable with what a lot of students would consider a very difficult topic. So, suppose you have the following items in your pantry. We go to a common pantry and we see these basic things, right? We got 4 cups of milk, 8 cups of flour, 12 eggs, 2 cups of water, and that is an infinity sign and an infinite amount of water, right? What are we going to make with this? Well, let's make pancakes with the following recipe. Let's say that we need 1 cup of milk, 3 cups of flour, 1 egg, 1 cup of sugar, and a half cup of water to make 6 pancakes. Now, this is obviously a made-up recipe. Don't go and try this because it would be terrible. But these ingredients will make this amount of product, these pancakes, right? Now, the beautiful thing about this recipe is we can actually write this recipe like a chemical equation, because chemical equations really are just a ratio of our ingredients that will make a certain amount of product. So we're going to go ahead and write this as a chemical equation, and we're going to use these numbers as our stoichiometric coefficients, like we learned back in balancing equations. Now remember, a balanced equation needs to have all whole numbers, so we're going to have to multiply all these numbers by 2 to get this 1/2 to be a 1. Here we go. So that would be 2 cups of milk, and I'm not going to write the word cups, I'm just going to write the ingredients themselves. So we got 2 parts milk plus 6 parts flour plus 2 eggs plus 2 cups of sugar plus 1 cup of water to make. Now we multiplied everything else by 2, we got to multiply this by 2 as well. It's got to make a dozen pancakes. I hope you're hungry. Here we go. Now the question that we can ask ourselves is, using this information up here, this is what we have in our pantry. And this is what our recipe is going to allow us to make. The question is, what's the maximum amount of pancakes we can make? So, max pancakes. The theoretical maximum pancakes. How many can we make? Now, since these are just integers, and this is a pretty straightforward question, you've done this math in your head before, you might look at the fact that, well, this is our recipe and this is what it calls for, this is what we need to use, and this is all that we have. Well, we have an infinite amount of water, so that's not going to restrict us. We have quite a few eggs. We only need 2 per batch, and we've got 12 of them, so we can make 6 batches with that. The flour seems problematic, but we have enough for at least 1 batch. And then the cups of milk, we can do 2 batches with that. But if we look at the sugar, 2 cups of sugar is all we have in our pantry. And we need 2 cups of sugar to make 12 pancakes. So at most, we can only make 12 pancakes. Why? Because when we're done making 12 pancakes, we will run out of one of our key ingredients. The 2 cups of sugar will be gone forever. And then the only way we can make more pancakes is if we find a way to get more sugar, because we're not going to skimp out on the sugar on our pancakes. That is the basis of stoichiometry and something we call limiting reagents. Since the sugar limited the amount of reaction that could happen, that is the limiting reagent. Everything else would be considered our excess reagents because they're left over. So that is about as hard as stoichiometry gets. The only thing that makes it weird is when we start talking about chemicals and equations and numbers that are not just sweet little integers, some math that you're going to probably need a calculator for, not something you can do in your head. So that's the basic reminder of our introduction there. But let's go take it to something a little bit more complicated. Let's take a moment to talk about stoichiometry in the context of chemical equations. So, first thing we always need with our stoichiometry is a balanced reaction equation. And I've already balanced this equation here for you. And that gives us these reaction components, our iron and oxygen, reacting to form iron 3 oxide. It gives each of these reaction components a ratio with each other, basically saying for every 4 moles of iron and 3 moles of oxygen, we will make 2 moles of iron 3 oxide. You can think about this in any direction. You could say for every 2 moles of iron 3 oxide that we make, I must use at least 3 moles of oxygen and 4 moles of iron. It's all a matter of perspective, and knowing how to read these equations, knowing how to make sense of these numbers is way more important at a base level than knowing how to read this question, okay? So we got to get used to that. Let's see here. If I completely react 10 moles of iron with excess oxygen, meaning if we ever see this, that means that we have more oxygen than we can possibly need, it will not run out. How many moles of iron 3 oxide will be theoretically produced? Well, we know that we only have 10 moles of iron, so that's going to run out. The question this is really asking is, once we run out of iron, how much iron 3 oxide did we make? Well, it's pretty simple. First thing you want to do is start with what you're given, right? So I have 10 moles of iron, and I'm going to put that as a fraction over 1. Okay. Now, something you want to be aware of here. I'm going to multiply this by what we call a conversion factor, right? Just like we did with dimensional analysis before, we're going to try and cancel out units of iron, moles of iron, and get units that we are looking for. Well, the question wants us to say moles of iron 3 oxide, right? So I'm going to put that up top. Moles of Fe2O3. And then I want to get rid of moles of iron. Well, if I put moles of iron in the denominator of the next term, when I multiply these fractions together, you're going to see in a moment that we can cancel out those units. So what are the numbers going to be here in this conversion factor? Well, how many moles of iron 3 oxide are made when we use a certain number of iron? Well, we use the coefficients for this ratio here. For every 2 moles of iron 3 oxide that we make, I must use 4 moles of iron. So when I multiply these two fractions together, I multiply the numbers and units across the top, and then I multiply the numbers and units across the bottom to make a new fraction. So 10 times 2 is 20, and then that's moles of iron times moles of iron 3 oxide. In the denominator, this number doesn't have any units, so that's convenient. 4 times 1 is, you guessed it, 4, and the units come along as well, moles of iron. At this point, you can just simplify the fraction. Well, we have moles of iron on the top and the bottom, in the numerator and the denominator, so we're going to cancel them out. And then 20 divided by 4, that is 5. So we are left with this as our answer, 5 moles of iron 3 oxide. Now here's the deal. What does this answer mean? What does this answer mean? That's more important than just finding the answer, is understanding what it means. If I completely react 10 moles of iron in this reaction, I will make, theoretically, 5 moles of iron 3 oxide. And the reason we say theoretically as a clarifier is that's in a perfect world. It's totally possible that if I did this reaction in real life, a little bit of iron might get sprinkled off to the side and we wouldn't actually react all 10 moles of iron, or something might go wrong. Maybe I'll get a little bit of water in there by accident and that'll make me have what seems like 5.05 moles of iron 3 oxide, though we know that's impossible because that would violate the law of conservation. So that's the basics of a mole to mole conversion, and we'll see more complicated scenarios like this where we convert between mass, moles, and then moles back to mass again. It's going to be a little bit more complicated down here, but if you follow the same basic steps, you'll be okay. So before we even start this question, I want to be clear about that. I'm going to show you this generic equation a lot. The mass of A, whatever A is, you can decide that, must convert then to the moles of A. And then from moles of A, you can convert to moles of B. And then for moles of B, you can convert back to mass of B. This sequence must be followed in a linear fashion. You cannot skip steps. You can't go directly from mass to mass. You can't go from the mass of A to the moles of something totally different. You need to follow this sequence in order. So you can model your calculation, like we multiplied fractions up here. You're going to model your calculation after this process as well. So here we go. If I completely react 40 grams, the mass of iron, with an infinite amount of oxygen again, what mass of iron 3 oxide could be theoretically produced? Same question as above, except now we're talking about mass, and we're trying to find mass. So if we start with what we are given, 40 grams of iron, I can set that as a fraction over 1. We are not going to worry about putting in any numbers yet. No numbers. We're just going to put in units. And we're going to follow this generic equation above. And I'm sorry, I wish I would have lined it up a little bit better. Here we go. You've got the mass of A right here. And just like we said in the question above, we want certain units. Whatever units we want, we're going to put up top. Well, if we're following this linear process, the answer is kind of given to you already. We're going to go from mass of A to moles of A, which in this case we define as iron. And then from moles of A to moles of B, well, what's the B that we're looking for? Iron 3 oxide. So we're going to convert that to moles of iron 3 oxide. Okay. And now from moles of B to the mass of B, we want grams of iron 3 oxide. So again, A in this case is iron, B in this case is iron 3 oxide, but the sequence must be followed as such. Mass of A to moles of A, moles of A to moles of B, moles of B to mass of B. Now, what do we put in the denominator? What are we going to put down here? How are we going to make sure that none of these units actually get into our final answer? It's very simple. Whatever the units are of the previous term's numerator, put them in the denominator of the next term. So here we go. We're going to say grams of iron down here, and then moles of iron down here, and then moles of iron 3 oxide down here. Okay, so far so good. Now you're going to notice something very interesting about these terms. We've got these two terms, which are a ratio of grams to moles of a certain compound. It's for the same thing. This is the molar mass of iron, written as a fraction. And this is the molar mass of iron 3 oxide, written as a fraction. And if we remember how to find molar mass, we have to use the periodic table. So I'm going to pull up the periodic table for myself here on ptable.com, one of my favorites. All right. It looks like we have iron is 55.845 grams per mole. I'm going to write that as a little box down here. Iron is 55.845. You don't have to do that as a box. It's okay. And oxygen, we're going to keep it real simple. We're just going to call it 16.0 grams per mole. That's what you'd find on the periodic table. To get the molar mass, well, we're doing a certain number of grams here per mole. Well, for every 1 mole of iron atoms, I'm going to have 55.845 grams. Cool. Now, what is this term here in the middle? This is our mole ratio, the ratio of our reaction components, iron and iron 3 oxide. Where do we get these numbers? We get them from our balanced chemical equation. They're already given to you once you balanced it. So there's our 4 moles of iron for every 2 moles of iron 3 oxide. And now to find this, we just have to say for every 1 mole of this compound, how many grams are in it? Easy. So we know that iron is 55.845 grams per mole, and oxygen is 16.0 grams per mole, times 2 times 3. And that total number will be the grams per mole of iron 3 oxide. Let me get my trusty calculator out, and I'll put it in the screen so you can trust me on my numbers here. All right, 55.845 times 2 plus 16 times 3. Bang. 159.69. Bang. All right. Now, just like before, the exact same process is going to happen here. I'm just going to put that down there so we don't lose track of where that came from. Okay. All right. I'm actually going to draw an arrow all the way down to here because I'm going to combine this as one big fraction for you, just like we did before, so you can see how all these units are going to cancel out and all the math is going to work. Okay. So just like we did before, we're going to multiply all the numbers across the top. What's 40 times 1? You know that. It's 40. And then you multiply that by 2, and then multiply that by 159.69, which is when I can't do that kind of math in my head. This is going to be a very big number, 12,775.2. Now, all of the units come with as well. So, grams of iron times moles of iron times moles of iron 3 oxide times grams of iron 3 oxide. Oh, that's a big numerator with a lot of units. Oh gosh, no, don't make it messy, Mr. Richards, come on. All right, there we go. Sorry, that's a really messy fraction bar. I'm going to try and embolden that. Okay. Now in the denominator, same thing. We have 1 times 55.845 times 4 times 1. Bang. All right, a much smaller number, but here we go. 223.38. And again, the units come with, here we go. We have grams of iron times moles of iron times moles of iron 3 oxide. Look at this big, glorious fraction. This is a big, big fraction, but we notice that we can simplify this fraction now. If the units are repeated in the numerator and denominator, they can be canceled out. Moles of iron cancels out, and moles of iron 3 oxide cancels out, leaving us with the only unit remaining, grams of iron 3 oxide in the numerator, which is key. And then the math for our numbers, we will say 12,775.2 divided by 223.38. Bang, 57.19. And you can keep it that simple. 57.19. You don't need to go to a billion decimal places. 2 is usually fine. And that is 57.19 grams of iron 3 oxide. Once again, what does this answer mean? Well, if we react 40 grams of iron under these conditions, theoretically, that's the most iron we could make. That's the best we could do. It's possible that we would be under that. It's possible with error that we could be over that number if we actually performed this reaction in a lab and measured it, which is something we're going to do, not necessarily with this reaction, but this is how we can prove how close were we to the theoretical maximum. And that is the basis of stoichiometry. I understand that these numbers and things are a little bit more complex than something like pancakes, but the principle is still the same. The idea is still the same. If you need more help with this, please let me know. I'd be happy to go over any extra practice examples with you. Please email me if you have any questions. Thanks for watching, guys, and I'll see you in class.